there's another mathematical aspect to this mechanism that the artist had to use to make it work the way he wanted. And if you notice, there's two gears involved here. There's a little tiny gear kind of in the middle of the mechanism. That's the one that's actually attached to the motor. So the motor drives that little tiny gear. And then there's a much bigger gear down below connected to it by a chain. And so why would the artist have to use two gears? Why wouldn't he just attach the motor to the arm that he wants to have rotate? And the answer for that lies in the concept of gear ratios, which is just another ratio, a theme that we've been talking about in a lot of these pieces. So you can see here we got two different size gears. And the gear ratio tells us a lot about how they interact with each other. And simply put, it's just the ratio in the number of teeth from one gear to the other. Or we can think of it as the ratio of the number of turns that this gear makes for each turn that this makes. So what we're going to do is I'm going to turn the top gear here, and half of you are going to count how many times this goes around, and the other half of you are going to count how many times this goes around, and we're going to keep turning until both of these arrows are pointing straight up again. So both gears will return to exactly the same position after a certain amount of time, and we'll calculate the number of turns of this compared to the number of turns of that, and the ratio between those two will be the gear ratio. So here we go. We'll turn this around, and notice, it's probably not too surprising, that the top gear is turning more quickly than the bottom gear. So this has already gone around exactly once. This hasn't gone around a full turn yet. How much has it gone around? Well, we'll see once we do the gear ratio. So we're going to keep going, and we'll just keep doing this. And I know you guys are counting until they're both pointing straight up at the same time. No, not there yet. There. Well, this one's straight up, but that one's not straight up, so we got to keep going. And it seems like it's taking forever. But, oh, there, we managed to do it. They're both pointing straight up again. And as you're counting, yeah, that's right. This one went around 5 times, and this one went around, 3 times. Okay, so we say this is a gear ratio of 3 to 5. And if we count teeth, we see this is 6, and that's 10. 6 over 10, we reduce that, we get 3 to 5. And so what does that tell us? For every turn this makes 3/5 of a turn. It also tells us that, if this takes a certain amount of time to go around, this takes 3/5 as long to go around. So now we could apply that up there. Now that top motor is a standard kind of motor. It might be going at something like 30 RPM, one rotation every 2 seconds. But if you look at the arm, it's going up and down more slowly than that. In fact, it takes 7.5 seconds for that arm to go up and down. So we can calculate what gear ratio would you need to turn a 2-second rotation of the little arm, the center arm there, into 7.5 seconds for a full round trip of the hammer. And the answer would just be 7.5 over 2, or a gear ratio of 3.75. So what this tells us is if, for example, the top gear has 8 teeth, and I don't know, I didn't count the number of teeth, we would multiply that by 3.75, and we'd say 30 teeth on the bottom gear. So that's one possibility. 8 teeth on the top and 30 teeth on the bottom would turn that 2-second rotation into a 7.5-second rotation. And another thing that the gear ratio does for it, just the way you talk about like with the map where that same ratio multiplies everything, it also tells us the multiplier on the force. So that little motor might not have enough oomph to move that big arm up and down, but because of this gear ratio, it's actually increasing the force, or technically what's called torque, when you take a physics class in high school, on the lower gear by that same factor of 3.75. So we get 3.75 times as much torque as well, and now that's enough to move that big heavy arm up and down. So that same ratio, like with the map we multiply everything by the same ratio, is multiplying both the time and the force that it can apply, allowing the artist to construct the artwork and have it work the way he wanted.